How do you start the first video in a 3-part series on stepper motors? I guess you just say steppers while pointing to one. Part 1 is all about the hardware. We all have these huge lumpy things on our printers, and I think it's about time we learned how they work and what's inside them. Let's go! So this is a stepper motor, obviously, but so is this. I would continue filling the desk with more of them, but I only have these 2 types in various sizes. These are the 2 dominant species of stepper. You will actually struggle to see many other types of them in the wild these days, which is kind of weird, but anyway, the left one is generally regarded as the general purpose, cheap, everyday throwaway stepper. And I think this is due to the fact you can buy them for a little more than a couple of pounds each, including driver circuits, which is just crazy. And the right ones are the more serious equipment that we tend to recognise from our printers. These ones will cost anywhere between a £5 and 20 quid, which, translated for non-British people, is between £5 and 20 pounds. What might surprise you though is that the cheapo 28BYJ stepper here actually has a higher resolution, and for reasons we'll find out in a moment, a strangely high ability to not slip when in use. Weird. But before I get into the whole opening up the stepper part of the video, I think it's worth doing some basic theory. All motors work by using the power of magnetism. In order to do that, you have to be able to command the power of magnetism itself, which isn't a particularly common special power. So we have to use a bit of physics. And nobody knows how this works less than I do, so I'll skim over it. If you run a current through a wire, you induce magnetism. It's not optional, it always happens, but we usually ignore it, except for when we purposely make coils of wire with lots of windings on them. This essentially makes an electromagnet. Ordinarily, a traditional motor will have one part that's a permanent magnet, i.e. a normal magnet, and the other part which is an electromagnet. But there's absolutely no reason why both sides can't be electromagnets. This is a thing, we just won't be looking at it. By the way, while we're on this topic, you may have heard the phrase brushless motor thrown around a lot lately. This is because they're getting very popular. I might as well explain it, as stepper motors are kind of the same thing. Well, they literally are the same thing. Stepper motors are a special type of brushless motor. A traditional brushed motor, like the cheap ones here, they have the magnets on the outer edge, and they are stationary, with the electromagnets being the bit in the middle. It's not hard to see that the electricity needs to get to the electromagnet windings in the middle, but that's turning, so you need some kind of connection. This is done by means of brushes that stay still. The advantage of this is that the motor can switch the circuit as it turns, and so that will continue to propel the motor without having to have any kind of driving circuitry. The voltage will reverse as it goes round, so it's a pretty simple way of doing it. And I guess you can't control the spinning speed, it just kind of reaches a natural equilibrium based on voltage versus friction, I guess. Brushless motors solve this electronically. If you put the permanent magnet in the centre instead of the wiring then is at the outside and it's stationary and there's nothing to wear out. But of course, if you think about it, sticking a battery, which is DC voltage, on those coils is not going to turn anything. The magnetic field is not going to be changing. So you have to drive that somehow with control circuitry, basically. It makes a lot more sense, but of course in order for these to become massively available and cheap, the circuitry had to be cheap. They are almost universally used in PC case fans, in case you're wondering why you feel like you already know about them. Anyway, that leads us into how steppers fundamentally work. They have the same permanent magnet core, but around the edge you have direct control of the magnetic coils, and unlike a standard brushless motor, with steppers you have to drive the coils yourself directly through the motor's pins. You have to send the waveform or signal that alternates the magnetic field to make it move, one step at a time. Hence the name. I could show you that. Here is a stepper motor. All I'm doing here is supplying power to the coils inside. If I switch the power around, the motor takes a step. Switch again, another step. Stepper motors have an unusual feature due to the way they work too. They spend a lot of their time essentially what would be considered for a normal motor stalled, meaning they are holding their position. They're happy to do this, whereas most motors aren't. They will eventually overheat. When you lock the axes on your printer, you are activating the steppers in this way. You're supplying the constant current to the coils and producing what's known as a holding torque or a stall torque. And yes, they do get hot doing this. Surprisingly, most steppers are actually okay to operate at up to 90 degrees C, sometimes further, which is why they come with these warning stickers. So when you jump on Reddit to ask if hot steppers are normal, well, if you can touch them at all comfortably, the answer is almost certainly yes, it's normal. At least kind of. You can see my previous video on belt tension for a bit more on that though. So I think it's about time we take this to bits. Inside there's exactly pretty much what we expected to see. There's a very heavy and strong magnetic core. And around the edge, there's coils. I suppose I have some explaining to do here because there's only 8 coils here, so how is the motor not taking bigger steps? If you reverse the magnetic field, why does it jump 1.8 degrees around and not 360 divided by 8, which is 45 degrees? That is in fact how a brushless motor works, and you can feel it when you turn them by hand. If you turn a PC fan by hand, you can feel the steps. But if you look at the stepper's interface between the coils and the core, we have here what's known as castellations. These, and as far as I'm concerned, magnetism, is basically magic. But what they do is they break up the magnetic force into tiny magnetic forces. It really shouldn't work, but apparently it does. By using these castellations, each electromagnet becomes 6 magnets, and the core has... Well, actually, I haven't counted them, but it doesn't quite line up between the inner castellations and the outer ones. You might spot that. There is a good reason for all this. On hybrid stepper motors like these, the top half is arbitrarily a north pole, it could be south, I don't know, and the bottom is the opposite pole. You can see that they're offset, and that is clever. Think about the castellations. When you charge one magnetically, it will attract the opposite side of the magnetic core, so it will repel the other. So the top and the bottom are offset, so they can be driven by the same magnetic field. That works really nicely. Let's move the stepper though while it's open. I've got a driver box here, which is just a standard off-the-shelf thing. These are quite cheap, and they're pretty primitive in terms of how they drive the stepper compared to how 3D printers do it, which we'll get onto in episodes 2 and 3. This box is just taking a simple pulse in, and it will turn it into the right kind of square wave to step the stepper 1 turn every time it gets a pulse in. So I can wire up a button to it, and every time I press the button, the box will advance the stepper 1 step. I'll show you the waveform in a moment, but it's not very clean from this source, so I'll get it from somewhere else. 1 press is 1 step, and you can see how the castellations align on 2 of the 8 groups simultaneously, and this travels clockwise around with every step. This is how the motor propels itself. The alternation of the voltage potential reverses the magnetic field between each step, and the logical thing for the motor to do is just to go where it's pulled to the next electromagnetic pole along. It's very clever. And that, by the way, is why there are more teeth around the edge than in the centre, to create that imbalance that makes this work. Obviously, normally you wouldn't drive a stepper motor 1 step at a time. In fact, that's pretty much exactly what you never do. They are incredibly accurate at taking a series of steps, an exact number of steps, to a location. They don't have any way, though, of knowing where they are. So this is why most printers have end stops, which they use to locate the printer initially when they first start printing. And this is why every move of a 3D printer's axes is done relative to the location that was ascertained at the initial stops. However, they are worked out throughout the whole print. Even if the print is days long, which is mind-blowing, the printer can still know exactly where it is because of the amount of pulses that have been sent to the stepper. Because what steppers do is they accurately move a specific number of steps. This is done by sending a specific amount of pulses, and I'll show you how they look now. Before I do that, layer shifts are the natural result of the printer thinking it knows where it is, but being wrong. But it's a testament to 3D printers that they're surprisingly uncommon. Anyway, I have an Arduino Mega here, which I've programmed to output a stepper signal. I'm powering the smallest stepper with this because it has a driver that's more of an amplifier than a driver per se. If I show you the pins here, these translate directly to the stepper's coils. The so-called driver board on these things are just something known as Darlington driver arrays. It just takes your input signal and it boosts the current to drive the motor. You could, if you could supply enough current, drive the motor directly from the Arduino, but you can't. Arduinos don't like doing that. The driver boards also have these really cool LEDs on them, so if you step slowly enough through, you can watch the sequence as it happens. On the oscilloscope, you can see the waveform. This is a 2-channel oscilloscope, so I can't show you all 4 pins at once, but you can see the separate coils signals out of phase with each other. I should be able to do some trickery to show you all 4, or maybe I'll just draw it on paper. And by alternating like this, you're sending a signal to tell the motor to slowly rotate 1 step at a time. Now, before I close up this episode, I also want to show you the inside of these cheap motors, because they're actually quite clever. Inside, you have a set of gears first. This is important, actually. But below that, you have the same kind of castellations as before, but as you can see, I hope, I did a pretty bad job of taking this apart. It's horrible and greasy. The whole thing is kind of turned on its side, with the coils stacked on top of each other, and again the same kind of magic is applied to the magnetic field through the spikes in these layers. they stack on top of each other. Counting the spikes tells you that, well, if it was assembled correctly, there's 32 positions for these steppers to be in, which is why the gears on the top that we saw are important. The gears have a 1:64 ratio, meaning that for a full rotation of this motor, the motors don't do 32 steps, but 32 times 64, which is 2,048 steps, meaning each step is 0.175 degrees, which is crazy small. It makes them slower, sure, but that's generally not an issue with most users of these motors. So that's it for this episode. Next time, I know that some of you are already leaving comments, what about microstepping, etc. It's all in the next episode, don't panic. Did I mess up the explanations? Probably, I usually do. Check the description for any corrections. If you have anything else to say, please do so in the comments. We will get onto more specific info about driving these things in the next episode, so I will see you then. Until then, thank you for watching.